Hello. As Regan said, obviously I'm going to talk to you guys about a image-based simulation workflow that we've added to in VirtualLab. So as well as working on the back end, I've been working on this as a side project, as it were. And it will help demonstrate some of the tools that we've added in, and you can sort of get an idea as to what VirtualLab is now capable of, and certainly how we've extended that over the last couple of years now. So, sorry, I skipped that slide there. Yeah, so this workflow is to do with component qualification, and that is a problem facing precision manufacturing. And it is, simply put, how do you know that what you're manufacturing when you get it off the assembly line, does this part behave the way you want it to? So say you need it to survive 200 pascals of pressure, and it has to be able to survive 600 degrees Celsius for 10 minutes or whatever. How do you know that what you're making comes off the assembly line and it's exactly that? Well, you can't really. So the traditional way to do this is to randomly get one part off of the line and say, this part here, test it, and go, does this work? Yes or no? Now that doesn't really tell you much. It tells you, does this part pass or fail the test? But if it fails a test, then does that mean every part fails a test, or does that mean just that part fails it? And when you deal with precision manufacturing, all kinds of defects become, it's wild how much the properties of material can change just based on micro cracks, pores, that kind of stuff we all sort of know about in the image-based simulation world. So it's a really good project to try and stick some image-based simulation into and see if we can solve this issue. So the basic workflow is this. Does this work? It does, yes. You've got design your component in CAD as you would normally. You then perform your simulations based on that to get your baseline and say, does this model work as it has it been well designed to work, and you get temperature out, get pressure out, whatever you're looking for really. You then get your component manufactured, and you take it off the assembly line and you perform a CT scan. At this point, you can then reconstruct that into an object in 3D space. You can then create a new CAD model from that reconstruction. And you can conventionally you can simulate it again, and then you can say, does this part perform as manufactured with all the defects, all the little cracks and pores and things? Does it perform the way I expect it to? Yes or no? There is also an alternative route, which is obviously because recent science, you can stick the simulation data and the CAD geometry into a neural network. And then from that, you can start to be able to predict performance very quickly without having to go through the step of CT scanning every part. You can just, you can create a CT scan and predict the performance in seconds rather than having to go through all the different simulations you were going to go through. So you can use the neural network to hopefully improve the speed and accuracy of this whole process. But for this particular bit, I'm only going to talk about a small section of this workflow, which is the bit that we've got working thus far in VirtualLab. Realistically, it's these two bits here, and that amounts to 3 basic steps. So you've got the X-ray CT simulations, we've got the image reconstruction in 3D, and then we've got the image segmentation. So, as Regan's already said, this is the same diagram again. I'm going to use VirtualLab for this demonstration, this workflow, and these are the 4 in red are the 4 modules I want to use. So we've got CAD-to-Box, GVXR, SIL, Servos. There is also an additional hidden package in there, which is I call image processing, which was a dumping ground for different tools, but I actually use a couple of tools out of there that we might put in a later version of VirtualLab once the next version comes out. So just be aware there are other modules in there that aren't necessarily visible to the end users yet, because we've been testing them. So first of all, before we start any further, you might notice I put green boxes here. Obviously, this is the image-based simulation conference, and there's going to be topics which are basic stuff to you guys, or at least some of you guys, but not all of you. So anything I think should be common knowledge, or at least is relatively common knowledge, I put in a green box. It's there for reference, so you can see here what is voxelization. Obviously, that's taking a triangle mesh and converting it into cubic pixels. But just so you know, bear with me there. I might touch on these, I might not. It depends on what I think everything I've covered, everything that I've put in boxes has already been covered somewhere else in this talk, on this conference. So hopefully I won't need those, but they're there for reference. If you don't know what voxelization is, for example, there's a brief summary for you. So on that topic, CAD-to-Box. This is a piece of software I've developed, and it's a Python wrapper for some C++ code. that performs, as it says on the tin, voxelization of meshes from CAD meshes to voxelization. The voxel meshes. It supports triangles, tetrahedrons, and it uses GPU with CUDA, and it uses CPU on OpenMP as well. It's open source. I've got it on GitHub. It's on the Python package on pip. Yeah, it's in Docker courtesy of VirtualLab. Hint, hint. There's also I should note now that the Linux only thing is no longer a thing. It's now on Mac OS and Windows. Although Mac OS is CPU only because CUDA is not a thing on Mac. So blame Apple for that one. But yeah. Also, there is a SYCL port incoming. That's hot off the presses, but that will be a while because I need to actually learn SYCL first. So I do plan to use it as an excuse to learn SYCL. So if you like your GPUs non-green, then you can you'll get to use that as well. So, but moving on. So other tools we've got on this list. I don't need to go into what GBXR is because Frank literally gave us a talk on what is GBXR. So yeah, that is available in VirtualLab. It's not quite the latest version, I don't think, because I'm not sure how far behind. Well, we're not far behind, I don't think, but we can update it as and when we need to. But there is a relatively up-to-date version of GBXR inside VirtualLab for you as a container. On that note as well, SIL is also there now. So that is obviously a Python framework for creating tomographic images. Again, anyone wants to know what tomographic imaging is, there's your brief summary there. But, I think a lot of people already know what that is. I won't cover that here. We've also got volume segmentics, or aka Servos 2. This is a package for doing image segmentation based on 3D data with everyone's favourite tool, machine learning, of course. It uses PyTorch and CUDA, and it was developed by Ollie King down in Light. It's now under A.V. Pendleton at the Rosalind Franklin Institute. And yeah, essentially, volume segmentics is the code underneath, which is what's in VirtualLab. The nice flashy GUI is also there, but that's Servos 2, and that's just a way to drive it nicely, and you get these pretty graphics. Have a look what you're doing and things. But yeah, again, anyone who wants to know what image segmentation is, that's the box there for you. So, last step then. This is the image processing stuff that I talked about. This is my secret module, as it were. It's basically a holding pen for tools related to image processing. In this case, we've got things like normalization tools because we need those for the experimental data we're using. We've also got registration tools. So, anyway, I don't think I mentioned the registration much this talk. Anyone wants to know, registration is how do you map one image onto another when they've got different geometries. So you basically, there's all kinds of techniques you can use. There's any manner of different tools. It's a bit of a rabbit hole on its own, that. But short version is VirtualLab has ITK Elastic in there, and wrapped by a thing called Simple ITK. Although simple is a bit of a debatable term there, but because this is not a simple tool to use, but it exists. And yeah, essentially you can do various different transformations to get one image onto another. In this case, we need it because the experimental data is never going to be perfectly aligned to the grid or to the center of your image, whereas our simulated data very much is that. So we need a way of mapping one to the other. So in our case, it's relatively simple. Just do translation and rotation and a little bit of scaling. We're there. So that's those tools also available now within VirtualLab. So with that said, back to Hive. I've decided to continue with Hive simply because it's all inclusive then at that point. So we've heard about the Hive experiments from Radiant's side. He's interested in the physics of the situation. I'm only really interested in the geometry. It's an interesting block thing. You can see it's a block with a pipe going through it, which is a bit more an interesting thing to work with. So essentially, it's a long metal pipe with a metal block in the middle of it all. It's made of aluminium vanadium alloy, I believe. So it's all one solid piece of metal. We're going to try and simulate X-ray CT of that. So you can see here's the mesh and parody. This is roughly what it looks like. So if we move on. So on to GBXR then. We've got these are the results we got out of this thing. They're not the best scans in the world. There's a big black. It's a big black block in the middle with a slightly more see-through pipe by the side. We did two kinds of scans in the end because initially Nikon, who did the CT scans for us, did a circular scan, which basically involves having objects you've got beam there, object there. You rotate your object around and get the various angles, various different projections that you then reconstruct. So the issue is the scattering was horrendous. It doesn't look bad in these images. That's because we're comparing different grayscale values on a projector, and you cannot see it. But believe me, it's there, and the streaking and artifacting is horrible. So we ditched that in the end, and they redid them in what's called a helical scan. However, GVXR doesn't natively do that, as far as I know. So in the end, I went for a slice scan to simulate that. So I just took the object and did a 2D slice, and then moved it down a little bit, another 2D slice, moved it down a little bit, another 2D slice, and just kept going until I covered the entire object, and then rebuilt it into a fake helical scan, as it were, in the reconstruction phase. So we'll start with the circle stuff. As you can see, you can see it a little bit. You've got really bad streaking on these sides here. But this is what still produced from GVXR data. And yeah, as you can see, it looks okay. You can see I've got a slice from the top there, so you can see the pipe. You've got the top of the block there, and that's the side view there. So again, you get the idea of what the junctions look like. And this is the actual CT, experimental CT scan of that object. Again, same thing. The contact is a bit different, but you've got that's from there roughly. You've got that one there from there roughly, middle of the pipe somewhere. And again, this is a side-on view. These lines here you can see are actually a sample holder. So they are not there in the simulate data because we're assuming the gravity doesn't exist, and you can have the object just sat right in the middle of a detector. Whereas in reality, obviously, yeah, that would never happen. So you need something to hold it up with. But so yeah, and that's what the circular looks like. And then these are my fake helical scan results. And as you can see, they're so much better. They have no more streaking going on. We've got rid of all that now. And also, you can even tell that the top and bottom of the object were cut off in the circular scan, and they're actually made of thinner metal. So in reality, you've got a little bit, the pipes are thinner at the top and bottom. And again, we've got several slices here. You can see these are actually pretty good simulated data. And that compares very well to the experimental data we've got. Again, you can see sample holder, but there's no more streaking, none of that mess anymore. And it looks pretty good. So what's next? Segmentation is in fact what's next. So we want to segment this data with volume semantics. So we use CAD2Vox. I've not actually mentioned it, I've realised now, but our CAD2Vox data looks like CT data, only it's very clean. It's just literally just clean lines because you either have an object or you don't, and the voxel data is very much cleaner than that. So we use that as a mask effectively to cover. We know where the object should be with the voxel mask, and then we cover the simulated CT data with that, and use that as a way of binary masking out which bits are metal and which bits are background. And then we took some subsamples, so we did three of them initially, and then and we ran them through the IBSim-4i. At this point, I should say I had 2 weeks to do this because my contract with Swansea ran out. So I had a go, and the results were, let's say, interesting. There was certainly something, let's say. As you can probably tell, we've got a blob. So that's the original CT data. That's the same slice. That's what our segmenter came up with. It's a blob. There's nothing else to say. It's terrible. And quite frankly, yeah, I was like, this is not great, but it's something. We have a segmentation. It has at least said there is something there, but you can't tell anything in the geometry at all. And I was a bit worried about this, I'll admit. But fortunately, Avery Pending's into the rescue because she had a look at this afterwards and got something very interesting. So this is Tara's first attempt. Initially, she decided to ditch the circle data because there was too much scattering going on, which was fair enough because that makes it even harder. So this is all the helical data now. I don't think we ever got circle data actually working, but so she produced these. These are the segmentations she got. So as you can see, you're getting pretty damn close now. The yellow line is what Volume Semantics reckons is objects. Obviously, we superimpose on top of that, underneath that, shall I say, the circle data, the helical data. And as you can see, it's a pretty damn good match. We've got a few issues. I mean, the corners aren't great, and there's a big wacky great hole in it. But we're getting somewhere. We actually have useful geometry at this point. And we use some post-processing as well, and we can actually get pretty damn close. That's just with 3 subsamples, and at 25% resolution. So we end up with something that's actually a very usable segmentation at that point. And AB went on further. So this is all seismically honest, but hence the animations. But, yeah, so we had a second attempt, 100% resolution. We didn't do much better actually. So it turns out resolution may not be as important as we think it is. But yeah, we got okay results. And then we did a third attempt at same 100% resolution, but with 1 big ROI rather than 3 smaller ones, which I think was 1/8 of the volume of the entire thing. And we got a better result, but we still need to post-process it anyway. So at this stage, the further investigation is required. I'm sure you'll hear about it in 2024, as and when you get to it. But yeah, it's certainly a lot better than my first attempt at it. So we'll go with that. So yeah, in conclusion then, I've demonstrated some of the part of an image-based simulation workflow within VirtualLab. I've walked you through an example of how this all works. So next step on that simulation workflow will be VoxCAD, of which there's a multitude of different softwares. I think there's even some already in VirtualLab actually, but and then we're going to try and integrate it with the machine learning side. I say we. I meant I'm more mean Bidian, to be fair, but that's the way it goes. So yeah, thank you very much. Just acknowledgements who the people who funded the work. And yeah, that's all I've got to say really. So thank you very much.